Good morning, Honor Statistics. This is Mr. Kim. Officially, this will be the first video for our remote learning. And this week, we're going to wrap up on 3.3. You guys have actually already done the assignments on Desmos activity for 3.3, talking about the residuals. And most of you guys have already done residuals in the previous project, not the one you just turned in last week, but the one before that way back in the past. It's just simple. There's a formula for you guys right here. You guys can all see what's going on. My main objective for this video is for you guys to understand the concepts in 3.3. Mostly it's about the residuals, how to interpret the S and the R squared and the outliers and such. There are a couple of ways in which you guys have to remember what we call, what I like to call them, the templates. When I ask you guys to write the open-ended section, like what to write down exactly, you write them down word for word. That is not negotiable in any sense. When they ask you to interpret something, there could be a little tweaks here and there, but I'll go over what I mean by that when we're talking about memorizing the templates as to what we say for S, R squared, and things like that. Okay, so these notes are available for you guys in the notes folder. Is where you will find the PowerPoint slides usually, but I'm using the Skew the Script package for you because it's just much easier for you guys to just print them out. And what I would like for you to do, if it works for you, just print this out and just kind of fill them in while I'm also going over this with you. So today will mostly be just writing down the notes, getting them out of the way, and you have a sapling assignment due by the end of today, or if not, just by tomorrow. Just make sure you have everything submitted. There's only 8 questions, so it shouldn't be that bad. So first, let me just talk to you guys about residuals and what it is. Residual is the error or the vertical distance between a linear model's actual and the predicted. So, but then we always just tend to say predicted, or prediction, let's say prediction, and the actual data point. When we find out the residuals, it's always important for you to know which one comes first. Y is the actual, and what Y hat, as we like to call it, is always the predicted. So we write it as Y minus Y hat for what we call the residuals. So for example, let's say I give you a scatter plot and I give you the best line of fit. The residuals will be from the dot to that line. So sometimes it might be a positive difference, or sometimes it could be a negative difference where the actual is actually below the line. So that is how you find out what we call the residuals. So if you answer these questions here, a student comes to the school, if its attendance rate is 80%, so we're looking at here, what is its predicted test score? We can estimate it to be somewhere around like maybe 37 or 38, depending on how you look at it. The student gets 44 questions correct on the exam. Find and interpret our model's prediction error. So let's say our actual is about 37. We want to find out our residual. So remember, residual is always your actual minus the predicted. So our actual was 44 and our predicted was 37. So we can say that that's going to be 7 for our residuals when you do that. I think for the notes, they said literally 37.91, closer to 38. But if we're really just eyeballing it, it should be somewhere close to being around 7-ish or so. You can use the equation also to figure out how many, star algebra 1 score that would be. So that would be a lot more accurate result. You just actually plug in 80% in there, get the value exactly, and then find out what the residual would be. This is just for your side note. If you have a positive residual, like I told you before, that means that your dot is above the line, like these points right here. But if you have a negative residual, it means your dot is actually below the line and things like that. So that's what this is talking about here. So this is where the main bulk of the lesson for today is going to be. It's called residual plots. And guys, residual plot is very different from scatter plot in the sense that it will always have a line, first of all, horizontally at 0. Residual plot only measures the residuals in a vertical sense. So we don't really have necessarily a slanted best line of fit. Rather, we have a line at 0 indicating that if the dot is actually on the line, you will have a residual of 0. So all these dots, for example, I mean, I kind of drew over it, but these dots right here, where they're on the line exactly, they correspond to the dots that are actually on the line, maybe, for example, these two, where the residuals quite literally are nothing. Like there's just zero residuals there. There's a high residuals like this one where there's a vertical distance that's very, very high, or there's a very low, I mean, there's a very high negative residual down in that direction. So it will always look in terms of like that, as you can see on the right-hand side. So the residuals are randomly scattered around zero without a pattern. Linear model is a good fit for the data. And I want you to kind of like highlight this and start how to put a star next to it. The reason for this is because they will sometimes usually ask you for questions like, is this a good fit for a linear model? A good linear model means that it's not going to have any of these random good linear scatter plot means that it's going to have a randomness. It's not going to have any patterns. So we're gonna say no to patterns when we're looking for linear model being the best fit of the data. So what does that exactly mean? It means that if I have, let's say, some sort of a curve, okay, if I were to put all the scatter plots together, and a curved line is a better sort of way to represent the data here, it's going to show in the residual plot. So for example, the residuals from here to there will be in the positive direction. Then you have it in the negative direction down here. Then you have a positive direction there. And it shows positive, negative, and positive residuals. And you can see that if I were to erase all of this, the residual plot also itself has this little curved pattern. Any curved pattern like this is, if it's and it's got to be an obvious curved pattern, that means that your linear model is not going to be the best fit. And it shows clearly also on the left-hand side as well. I mean, these dots right here in the scatter plot, they're not really best well represented with a straight up linear function. Rather, there's a curve here and that it's represented more by an exponential function. So residuals show a curved pattern, which means linear model is not a good fit for this data. So that's just the main, that's just it. If you have a curve in your residual plots, you're going to say, nope, linear model is not appropriate for the data. There's also another way of writing the residual plots, using the residual plots to determine if the linear model is a best fit or not. So take a look at this last case scenario where we have a bunch of scatter plots kind of being more scattered towards the end than beforehand. Obviously, you might assume that the linear model for in the beginning part would be okay because all the dots have very relatively small residuals, but it slowly starts to span out. And then you can also see that in the residual plot on the right-hand side. Now, what does this entail? It means that more variation, that's the word that they used. So more variation in the residuals as x values increase, linear model is still not a good fit. This is still considered a pattern, if you will. So there's not a curve per se, but if there is more data scattered throughout the end than before, and as you can see here, a linear model is not a good fit because, in the beginning it might be okay, but then it slowly starts to show a little bit more of a curve patterns there or maybe a line is definitely not going to be a good fit because it's going to create more and more and more high residuals at the very far end. Remember, the best line of fit, we call it as least squares regression line. We want to mitigate or minimize the regression or the difference between the dot and the line as much as possible. So this towards the end line is not a good fit. We want to make sure we can use some sort of other ways to do it, like such as curve patterns and things like that. So that is where it comes down to. So 2 case scenarios, mostly you will see like this type of stuff where, hey, if you see a pattern like a curve, don't say linear regression is the best fit. Only when you see a whole bunch of complete randomness, that's when you say that a best line of fit will be the best way to go. Okay. All right, so the next part here is we're going to have a standard deviation of the residuals. I'm going to use the notes here. So standard deviation of the residuals is typical error between the data points and their LSRL, typical, residual length. I don't want to use my own definitions because then it's going to confuse you guys. So I'm just going to copy and paste from the notes, but I'm going to just go over in detail as to what this is talking about. So standard deviation, as we already know, is like measurement of variation of all the residuals combined. So if I have a small standard deviation of the residuals, that means our data points are at relatively very, very close to the data. And if I have a very high standard deviation of the residuals, that means relatively speaking, all those dots are generally farther away from the line, the best line of fit, as compared to the previous model would be. So a stronger correlation means that it's going to be a smaller S, which means a strong correlation measures how the dot and the line is measured. Are they really, really close to each other? So if they're closer to one another, that means that the residuals will be decreased. It will be smaller. So your smaller standard deviation will be the result. Weaker correlations means that the dot will be further away from the line. So then we're going to have a larger S for this one. All right, so standard deviation of the residuals between test scores is S equals 1.99. Interpret this value. This is the type of question that I might ask you on your open-ended. So what do I say in cases like this? Well, if I ever ask you to interpret the S value, this is the template that I want you to highlight and memorize. So here's what you're going to say. When using the LSRL with explanatory variable, well, what is the explanatory variable? The explanatory variable is your X, right? So you will say with percent of schools attended, school days attended, to predict the response variable, which in this case, STAAR, algebra 1 test scores. So when using the best line of fit to predict between these two variables, we will typically be off by about 1.99. That's the value that we want to use for S. 1.99 with units of the response variable, which is the scores. So 1.99 points, and then period. That's it. So the part that's been underlined for you in this template is your job to fill those in with the context that's provided. Rest of them, you copy and paste exactly. When using the LSRL with percent of schools days attended to predict star algebra 1 test scores, comma, we will typically be off by about 1.99 points. That's what the standard deviation definition is. And this is how the college administrators for the AP exam, they want it this way. Or even in honest statistics, there's really no way about going about this other than just memorizing the template and filling them in. So interpreting the S, this is what you would say. And there's a couple more ways in which we are going to write this down as well. So on the next page, I think this one, we're just going to skip it other than the fact that saying it's just measuring the standard deviation for different things like public school mass shootings versus video game sales, mental health, and rifle production. So I will also upload a link to the video in which what explains and how to compare the standard deviations and things like that to different response to the explanatory variable and measuring them and making comparisons. Okay. So compared to mental health, rifle production is the much more stronger indicator because of the standard deviation being a lot lower. So if the standard deviation is higher, it means that there's a less correlation between those two. So it's just an application of how S could be used to interpret and make conclusions based on the data. That's what this page is about. Next, so here what we're going to do is let's take a look at all these R squared values. And R squared values for all of these things, I'm just going to copy and paste it. 0.83, 0.23, that's obviously 0, that's 1, 0.83, 0.23, like that as well. So it gets rid of the negative, obviously, right? Emphasizes the difference in the strength. Stronger the strength, then obviously the stronger the R squared value is going to be. So the whole reason why we want to actually square it is to really just get rid of the negative sign and compare in terms of relative strength and just solely looking at the values themselves, and we can make comparisons. Obviously, R equals -1, R equals 1. You might think, oh, wait a minute, -1 is obviously lower, but it's lower in a sense that it's negative and it's like one of the, it's strong. We still consider -1 as strong. So that, but -1 is different number from +1. So how do we make simple comparisons? Just fix the problem by squaring all the numbers. By squaring it, the higher the number it will be, the greater the R squared will be, which means it's going to be it's going to contain greater strength and correlation. Remember, R squared is anywhere between 0 to 1. So it's going to be easy to compare because any number that's closer to 1 will be higher in strength. Close to 0 will be weak correlation, and closer to 1 will be strong correlation. So again, STEM for interpreting R squared. We call it, they call it STEM. I call it the template. So R squared percent of the variation response variable can be explained by the linear relationship with explanatory variable. So this right here means that all of the points are actually on the line. So the linear model completely explains the data's pattern. I think they also said completely. 100% of all the data can be explained by the line. Now some of the dots are obviously not according to the line. They're not following exactly on the line, but this is 72%. If I have an R squared of, let's say, 72%, that means, or 0.72 for that matter, the linear model explains some of the data's pattern, or just a little bit. R squared value 0.72, it's not obviously on here, but it's a moderate level strength. So we can say that some of the data, the difference can be explained by the least squares regression line. All right, so here we have a value of 0.62. So it says interpret this R squared value. So how do I interpret it? Well, here's what you're going to say. You're going to use the stem. 62% of the variation in the response variable here is actually the US public mass school shootings. So US public mass shootings, oh, it's not school shootings, it's actually just mass public shootings, can be explained by the linear relationship with explanatory variable. With explanatory variable mean the number of rifles produced, number of rifles manufactured. Linear relationship with number of rifles manufactured. So let's do the little underlining. 62% is underlined of the variation of the US public mass shootings can be explained by the linear relationship. So that is your response variable, can be explained by the explanatory variable, which is the number of rifles manufactured, period. And that's it. You just have to use the template and then just copy and paste it exactly. That's how you would interpret the R squared value. It measures, or it talks about how much percent of all the dots with the line can be explained. The variations can be explained by the line. All right, so going to here, video games were the strongest indicator, predictor, I'm sorry. We can see that by using the R squared values. If the R squared is actually generally higher, that means it's much more highly correlated between the response and the explanatory. So the relationship between S and R. So if it's a strong relationship, we should have a low variation of the standard deviation, but we should have a very high correlation. And vice versa. If I have a very weak correlation, I'm going to have a very weak, also low R squared value, but we're going to have a very high S value, high variation due to that. Okay. All right. So here, which of the model file has an outlier? Well, the outlier obviously is by this, or it's by this. And you can explain your reasonings for this one, but I'm just going to skip for the outliers here. And the effects of outliers is something that we're going to be just talking about towards the end. This part right here, along with all of this, I'm going to just kind of skip and going over, but I'm just going to fill them in for you guys. The 2017 was an outlier data, was unusually far away from the LSRL. So this point is an outlier compared to this data and to this data. They're exactly the same. But now what's gonna be the effect of that, adding of that one extra outlier there? We're gonna be talking about this more in detail in the next chapter. But with the outlier, obviously your R squared is going to go, R is going to go down because now all the points are not really relatively close to one another as before. So you can see that from the data as well. That also in effect decreases the R squared value because you're squaring a smaller number. And your S, your deviation, your variation will increase because look at how great of a residual that creates, which adds a very high end level of residuals towards your standard deviation. So your standard deviation of the residuals will be very, very large. It got larger from before. So R squared, and S are not resistant to the outliers. As you can see, they all change. Outliers, I think outliers lower the strength of a relationship, obviously, because they are all kind of nice and intact and close to one another close to the line itself. But then this one extra outlier just creates a mess because it just creates a massive residual that just kind of disrupts the entire data. So making R smaller, this smaller, and S larger. I think that's also the words that they said. The discussion, we're gonna skip it, but like I said, I'm gonna post a YouTube link video as to explaining all these studies based on the statistics. What I want you guys to take for a grain of salt is just how to solve the questions. The main two big takeaways is how to write down the templates by asking you to interpret S and R squared. And also, please remember that the randomness in the residual plot is what you're looking for. Okay, so hopefully this kind of summarizes a 3.3. Tomorrow or the day after, we'll go over 3.4. Next week, in the first half of next week is when we're going to actually have our test. I haven't set up a date yet. This week, don't worry, we're just going to keep on knocking through chapter 3 one by one, the sections there. And we should slowly start to wrap up, and I'm going to give you plenty of review questions before the test. All right, so thank you guys so much, and I'll see you guys tomorrow.